Hello math friends, this is AP Calculus section 1.2 day 2. Today we are going to be talking about combinations of functions. So we have two functions, we'll call them f and g, and we could combine these two functions together in different ways to create a new function. And these operations that we can do would be addition, subtraction, multiplication, and division. So we have the sum and difference functions up here and the product and quotient functions as well, and what that means. Now, whenever we combine functions together, we always want to think about the domain of this new function that we are creating. So if we call the domain of f of x a and the domain of g of x b, then if we add f of x plus g of x, the domain of that new function becomes the intersection of their domains. Remember that upside down U stands for intersect. So in order to figure out what that is, we have to know what is the domain of our first function, what is the domain of our second function, and where do those two domains overlap each other. Because that overlapping region, that's the intersection, that's where the new function's domain will be. And that is the same for the difference of two functions or the product of two functions. Now, where it gets a little bit different is when we're looking at dividing f of x by g of x or g of x by f of x. We still have our domain as the intersection of the two domains. However, we do have to be careful because whichever function is on the bottom, in this case in the box, g of x is on the bottom, we can't ever let g of x be 0 because we know in math we're not allowed to divide by 0. So that might slightly tweak the domain that is the intersection of these two domains. And when we do our example here, we'll talk about that and we'll see how it is affected. All right, so for example 1, we're given two functions, f of x and g of x, and we are asked to find the addition of them, the subtraction, the multiplication, and the division, and their domains. Okay, so first of all, I want to make a little note here, and this is always going to be true. Always do your domain work first. So we want to figure out what our domains are. Well, our f of x function is the square root of 3 minus x. Since we have an even root, we know that the domain here has to be that what's under my root, which is 3 minus x, that has to stay greater than or equal to 0. And so if we were to add the x over to the other side, we would have 3 is greater than or equal to x, or if we flip that around, x is less than or equal to 3. So this is what we're going to call a, right? That's the domain of f of x. And then our second function that we're working with is g of x. And g of x is the square root of x squared minus 1. Ooh, this is another one of those quadratic inequalities, right? Because our domain here is going to be that x squared minus 1 has to be greater than or equal to 0. And in factored form, x squared minus 1 is a difference of squares, so that's going to factor into x plus 1, x minus 1 has to be greater than or equal to 0. Remember, this requires some sign charting. So I make a quick sign chart. We don't have to do a ton of work here, but we have to do enough to make sure that we have the right domain. So right there, we've got our two values that make it 0, and we can have it equal to 0, so those will be included. The question is just, basically, is it the part in between negative 1 and 1, or is it the part less than 1 and greater than, or less than negative 1 and greater than positive 1? So let's plug some numbers in and let's find out. If I were to plug something smaller than negative 1 in, say negative 2, negative 2 plus 1 would be negative, and negative 2 minus 1 would be negative. But then we're multiplying a negative times a negative, which means that this region would be positive. In the middle, if we plugged in 0, we would end up with a positive times a negative, which we know makes a negative. And if we plugged in positive 2, we would end up with a positive times a positive, which we know is positive. Now, if we're looking for values that are greater than or that make this inequality greater than or equal to 0, right here, we are looking for the positive regions. So that tells us that b, our domain of g of x, is going to be from negative infinity up to and including negative 1, union positive 1 up to infinity. All right, so now that we have our two domains, we are able to determine the intersection, okay, because that's going to be the domain of all of our new functions, basically. So it is easy to see A intersect B if we look at where the graphs overlap. Okay, now I'm sure some of you are asking me, or are asking yourselves in your mind, do I actually have to graph this? I think I can figure this out in my head. And you may be able to, but for those people that need a visual, that's what this is for. So let's graph A, which is the domain of g of x. And basically that is all values of x that are greater than or equal to 3. So here's my 0, 1, 2, 3 right here. Or sorry, excuse me, less than or equal to 3. Sorry. So negative 1, negative 2, negative 3. And of course, this continues in both directions. But that represents A, which is the domain of f of x, right? All values that are less than or equal to 3. So then we graph B right below it. And B, we know, I'm going to try to line my number lines up so that they look the same here. So here's negative 1, and here's positive 1. And for B, we know that our domain is negative infinity to negative 1 and positive 1 to positive infinity. So the question then is, well, where do these intersect or overlap each other, right? And that's the A intersect B part. That's what we're looking for. And that A intersect B is basically going to happen right here and from here to here. Okay, so A intersect B is going to be, if we write it in interval notation, is going to be from negative infinity up to and including negative 1, union 1, including 1, up to and including 3. Okay, so that is going to be our A intersect B. That's going to be the domain for all of these new functions that we're about to create. So all of the work that we just did was just to find the domain. We haven't even done any of these combinations of our functions yet. But this was the hard part. The combination part is the easy part. All right, so my two functions were f of x is equal to the square root of 3 minus x, and g of x is equal to the square root of x squared minus 1. And so the four combinations that they asked us to find were f plus g, f minus g, f times g, and f divided by g. F plus g is just going to be the square root of 3 minus x plus the square root of x squared minus 1. And we can't do anything to combine those. Okay, so this is going to be our answer. And the domain here is just going to be what we found, which is negative infinity to negative 1, square bracket, union 1 to 3. Okay, so this is f plus g in its domain. F minus g is going to look almost exactly the same except a minus sign there, right? And then my domain, again, is going to be exactly the same. That's why we do the work ahead of time. F times g, we're going to have the square root of 3 minus x times the square root of x squared minus 1. But again, we're not going to worry about simplifying this at this point. And the domain is going to be negative infinity, negative 1, union 1, 3. All right, last one. This one's the most interesting one. So we've got f divided by g. So in the top we have the square root of 3 minus x, and in the bottom we have the square root of x squared minus 1. All right, but now here's where things get different, okay? So we're going to make a little note here. Because g of x is in the denominator, x cannot equal plus or minus 1 because those values would make the denominator z, or 0, excuse me. Okay, so now we have to exclude those from our domain. So our domain now is going to change slightly, okay? It was negative infinity up to and including -1, but it's not going to include -1 anymore, so now we need to change that to a round bracket. Union, and it was including 1 up to and including 3, but we can't include +1 anymore, so that is also going to change to a round bracket. So just calling attention to the fact that this bracket and this bracket have now changed to round because we can't include +1 or -1 in our domain. So that's what makes the division part of this problem slightly different. Next, we're going to talk about compositions of functions. Two functions, f and g, can be combined together by substituting one function into the other. This is called composition because the new function is composed of the two original functions. And the most common way that we see this written is this, a lot of people call it the fog notation. It's that little open circle. It looks like the word fog, except the circle's really tiny, f of g of x. And what that really means is that you're plugging g of x in for the variable in f of x. So that's really f of g of x written in the parenthesis notation. And before we do this, we should also talk about domain. For composition functions, if, again, we call the domain of our first function f of x a, and we call the domain of g of x b, then the domain of f of g of x, missing a parenthesis right here, sorry about that, is the intersection of the two domains. F of g of x is defined wherever both g of x and f of g of x are defined. All right, so for this example, they're just asking us to find 4 different compositions. Well, as we said in the last problem, we should do our domain work first. But for this one, it's going to be pretty easy because if we look at f of x is you could think of it as a polynomial function, or you could think of it as a power function with a transformation. Either way, the domain here is going to be all reals. When we look at g of x, we have a linear function, 2x plus 1. Once again, the domain is going to be all reals. So all reals intersected with all reals means that the domains of our compositions for all of these are going to be x equals all reals or negative infinity to positive infinity. So for this particular problem, domain was easy. All right, let's take a look at these compositions. We'll start with f of g, which means that we are doing f of g of x. Order is important with compositions because we are plugging g in for the variable in f, okay, which is not the same as g of f of x. So we're going to start with our outer function, f, which begins with the variable squared. So something squared minus 1 is my f of x, but now I have to plug g of x in for that something, in for that variable. So I put my 2x plus 1 inside my parentheses. And then, of course, I can do some simplifying here because 2x plus 1 quantity squared, that's going to be a FOIL. That's going to give me 4x squared plus 4x plus 1. And then I have the minus 1. And when I combine like terms, the minus 1 and the plus 1 cancel, so I'm left with 4x squared plus 4x as my final answer. All right, next they want us to do g of f, which is the other way. So this time our outer function is g and our inner function is f. So our g function begins with 2 times something plus 1, right? 2 times something plus 1. And the something is going to be the f of x function, which is x squared minus 1. So that's what goes inside my parentheses. And then I should do the distributive property. So I'm going to distribute that 2. That's going to give me 2x squared minus 2 plus 1. And when I combine like terms, I end up with 2x squared minus 1 for my final answer. All right, next we're going to do g of g. And I know that that may sound kind of weird, but that just means that we're plugging the g function into itself. So start with g, which is 2 times something plus 1. 2 times, oops, I apologize. I should go back and say that this is g of x. There we go. Okay, so 2 times something plus 1, but the something is g of x again. So that's just 2x plus 1 inside that parenthesis. So then I distribute my 2, and I get 4x plus 2 plus 1, and I combine like terms, and I get 4x plus 3. And then finally, I'm going to do the same thing for f of f. This is f of x, which means I'm plugging f into itself. So f of x starts with something squared minus 1, and that something is f of x again. So it's x squared minus 1 minus 1. Well, x squared minus 1, quantity squared, is a FOIL. So when I FOIL that out, I get x to the 4th minus 2x squared plus 1, and then I have my minus 1. And my plus 1 and my minus 1 cancel, so I am left with x to the 4th minus 2x squared. And then again, we should put a little note here that the domain for all is what we would call A intersect B, which is x equals all reals, or if we wanted to write it in interval form, negative infinity to positive infinity. Now we're going to change gears a little bit, and we're going to talk about graphical addition. You can obtain the graph of a function f plus g, so basically a combination, an addition combination of two functions, by adding their corresponding y coordinates. Now the only time that you would do this is if you were asked to do it on a graph, like we are here in example 3. So it says add the graph of f plus g to the coordinate plane. Well, before we do that, we're going to need to find some points that lie on the curve of f plus g. So I am going to build a table to begin with. I'm going to have my x values. And then I am going to have my, and I'm going to color code it because that'll make it easier for us here. I'm going to have my f of x values, which are going to be kind of this, I'm trying to match with the picture here, kind of this purpley color. Okay, so this is what f of x is. And then my g of x values are going to be blue. And my f plus g of x, I'll do orange. All right. So now we just need to fill in our table. So it looks like, if we just look at the domain of the functions that we have here to work with, it looks like we're going to be looking at x values, and I'm just going to darken my x-axis and my y-axis because sometimes that's a little bit hard to see. It looks like on the left-hand side, -1, -2, my graphs go to -4. And then on the right-hand side, it looks like one of them goes to 3 and one of them goes to +4. So we'll go -4, -3, -2, -1, 0, 1, 2, 3, and 4. Being very thorough here with our table. And now to get our values, I am simply going to look at the picture and make an estimate of what the y values are on each curve, and I'm going to fill those numbers in on my table, and then I will add the f of x plus the g of x to get the f plus g of x. So when x is -4, it looks like though on the pink curve, it looks like my y value is -2, and on the blue curve, it looks like it's about +2.5. So if I were to add those together, I'd be at 0.5, right? Then when x is -3, it looks like my pink curve has a y value of -1, and it looks like my blue curve has a y value of +2. Adding those together, you get +1. So you can kind of see what I'm doing here, I hope. For the sake of time, I'm going to go ahead and I'm going to fill in this table quickly. When x is -2, f of x is 1, g of x is 1, and f plus g is 2. When x is -1, f of x is 2.5, g of x is 0.5, and f plus g will be 3. When x is 0, f of x is 3, g of x is 0.5, and f plus g is 3.5. When x is 1, f of x is 2.75, g of x is 1, so f plus g will be 3.75. When x is 2, f of x is 2, g of x is 2, so f plus g will be 4. When x is 3, f of x is about 3/4, or 0.75, g of x is 4, so f plus g will be 4.75. And then finally, when x is 4, f of x has a value of -1, but g of x does not have a value. The graph does not exist. DNE does not exist when x is 4. So you can't add two functions together in a location where one of the functions does not exist. So this is also not going to exist on my combination, my addition combination function. All right, so now that I have my points all filled out in my table, I'm going to go ahead and I'm going to plot these points so that I can draw the f plus g curve. So when x is -4, f plus g is 0.5. When x is -3, the curve is at when x is at -3, the curve is at +1. When x is at -2, the curve is at 2. When x is at -1, it's at 3. At 0, 3.5. At +1, 3.75. At +2, 4. At +3, 4.75. And that's as far as we can go. So then I just connect these dots as smoothly as possible. And there we go. That orange line represents my f plus g function that I added the f and the g together to create. The last part of our notes today talks about decomposing functions. And decomposing functions basically means that you are rewriting probably a more complicated function or a function with multiple processes within it as a set of simpler functions. So this is basically the undoing of a composition. It's like trying to pull the pieces back apart. What did you plug in and what did you plug it into? That's the idea here. When decomposing functions, you need to identify the inner function, what is being plugged in, and the outer function, what it's being plugged into. So when we're doing a problem like this, kind of the key is you want to look for parentheses when trying to identify the interfunction or the inner function. All right, so if we look at our first example here, number 4, it says express the following function in the form f of g. All right, so that means that there has to be an inner function and there has to be an outer function. Remember that f of g means f of g of x. So in this case, g of x is the inner function, and f of x is the outer function that we're trying to find. Well, I said look for parentheses when you're trying to define or to identify the inner function. Well, inside our parentheses, we have 2x plus x squared, and then that whole thing is being raised to the 4th power. So it's pretty easy to see that our inner function, or in this case, our g of x, is the 2x plus x squared, and then our outer function is something being raised to the 4th power, right? X being raised to the 4th power. And you can always check your work. If you plug g of x in for x in f of x, do you get the original function that they gave you? And the answer is yes, you do, right? So let's check it. If we were to check this, f of g of x would be equal to something to the 4th power, and that something would be 2x plus x squared. So that one works. Example 5 is a little bit trickier because they want us to express the following in the term f of g of h. Okay, well, so now we're composing 3 functions together. So let's talk about what this means. F of g of h means f of g of h of x. So h of x is the inner function. G of x is, we'll call it the middle function. And f of x is the outer function in this case. All right, so we're dealing with h of x equals secant of the square root of x, and that is to the 4th power. Okay, now I'm going to rewrite this as secant of the square root of x. This whole thing is to the 4th power because that's actually what that means. Remember, with trig functions, we always put the exponent in between the function and what's inside of it. It's just common notation, but it really means that secant is to the 4th power in this case. So if you start on the outside and you work your way in, it looks like our outer function, or f of x, is just going to be, and I'm going to write it down, f of x is just going to be something, in this case, x to the 4th power, right? And then the middle function is the trig function, is the secant. And then the innermost function, little h in this case, is going to be the square root of x. So now if we were to check this, so let's check it and make sure that it works out. If we started on the outside, okay, we would have something to the 4th power, right? And then the inner function would be the secant of something. And then the something that would go on the inside, the innermost function, would be the square root of x. So working backwards, it does work. I do end up with what I started with.